Hello, I'm John Frensley, and I'd like to talk to you a little bit about geometric scaling and density as introductions to a unit on fluid dynamics for AP Physics 1. I'm going to talk through the notes here a little bit, and then in a separate video, I'll talk about my density labs and activities. Okay, so in fluids, students are going to have to deal with situations where they're going to look at similar plane 2D shapes or similar 3D solids that are similar to each other, and they need to be able to make a claim about how the area or volume compares, usually not as an end of itself, but as part of solving a problem, right? And you'll see what that means as we go along. So I do this as an intro. It's a good time for it. There may even be a better time for it earlier in the year, but definitely if you don't do geometric scaling for now, do it now. Okay. So what I ask the students to do is just think to themselves and say, okay, I want you to fill in these areas of each of these shapes, assuming that L is the length shown. Now, these I give them, okay, because they're going to establish a pattern. We know that a square is L squared, L times L. We know that the isosceles right triangle is half of a square, so it's 1/2 L squared. Okay, what about this one? This will be L base times 1/2 L height and 1/2 that. So 1/2 base times height. 1/2 base times height. So that'd be 1/4 L squared. Okay, we know that this would be pi times the radius squared, pi L squared. This is going to be half of pi times what's this right here. That is half of an L. So that's 1/2 L all squared. So the squared goes the L, L squared. The squared goes the half, 1/4. 1/2 times 1/4 is 1/8. So this will be pi over 8 L squared. Now, what do I want the students to take from this? Note that every area equation has the same form, a constant times L squared. So L squared, the constant is 1/2. L squared, the constant is 1/4. The constant over here was 1. Pi is the constant L squared. Pi over 8, radical 3 over 2. 3 radical 3 over 2. 2 plus 1, 2 times 1. They're all some number times L squared. That's the key, that every area can be expressed as a constant times one of the lengths squared. Okay, now, it depends on the shape. And the shape does not have to be a nice geometric shape either. It can be an ugly, irregular shape too. Suppose you scale the shape by a factor n. What does that mean? That means you multiply all the lengths of the shape by n to make a similar shape. So all these lengths are multiplied by n, all these are multiplied by n, n. When you scale up a circle, the radius is multiplied by n, and the diameter is multiplied by the same n, and the circumference is multiplied by the same n. Okay, if the original shapes area was old area, what would the new shapes area be? Well, it would be the new area is the old area multiplied by n squared, because the L is squared in every single formula for area. In every formula for area, the L is squared. So what that means is that if you double the length of a square, that's 4 times the area. Double this length, which means doubling all the lengths to make a similar shape. It has to make a similar shape. Then the area is 4 times as much. If you make the radius of the circle 10 times the radius, that's 100 times the area. If you make this diameter 10 times as much, that's 100 times the area. If you make these L's all 3 times as much, that would be 9 times the area. That's what I want students to take away. Explain why the new area has this dependence on Aaron, because all area formulas depend on L squared, or you can say depend quadratically on length. So if you have what's called a quadratic dependence, then that means that if the independent variable goes 1, 2, 3, 4 times as much, then the dependent variable that's quadratically dependent goes 1, then 4 times, then 9 times, then 16, then 25 times as much, right? That's what I want students to get from this. Okay, all 4 gray shapes, right, are similar to each other. Explain how this series of shapes support your equation up here. Okay, look at this. This is one triangle. 1, 2, 3, 4. That's 4 triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 9 triangles. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. That's 16 triangles. If this is L, then this is twice the length, 3 times the length, 4 times the length. right? So as the lengths are multiplied by 2, 3, 4, the areas are multiplied by 4, 9, 16, showing the what I call the L squared, the length squared dependence. So I want students to know that if you make a similar shape that's twice in every length, that's 4 times the area. If you make a similar shape that's 4 times in every length, that's 16 times the area. That's what I want students to know. They're going to need that in order to handle fluids, all right, easily at least. Now, for solid objects, it's now not quadratic, it's now cubic, hence the term cubed, right? So what is this? This is the volume here is L cubed. This volume would be L times L times L, but only half, like the area of the base times the height. The area of the base is 1/2 L squared times the height of L, so it'd be 1/2 L cubed. And then this is 4/3 pi L cubed, right? And then what would this be? The area of the base would be pi times L over 2 squared. Did I do this correctly? I think I did it correctly on my key. And then, okay, that's the area of the base times the height. So the area of the base would be 1/4, that's the half squared, pi, 1/4 pi, or pi over 4, L squared, times another L for the length. So it'd be pi over 4 L cubed. Okay, and then here are some formulas I got from Wikipedia. But the bottom line is, in every case, it is the length cubed, the length cubed, the length cubed, the length cubed, the length cubed. It's the length cubed, right? Note that every volume equation you wrote has the same form. A constant that depends on the shape, L cubed. Okay, suppose you scale this up by factor n. Scale factor means that all the lengths are multiplied by the same number. So if you multiply all the lengths by 3, the scale factor is n equals 3. If you multiply the radius, which multiplies the diameter, the circumference, and everything else by 4, then that's a scale factor 4, right? All the lengths go up by the same scale factor. But the new volume is the old volume times n cubed, because it's a volume. Volume goes by cubes. So I have some ball bearings, okay? They're about 1 inch in diameter. But my 2-inch diameter ball bearing has 8 times as much volume and 8 times as much metal in it and 8 times as much mass. And if you buy the ball bearings, you can actually show that. You can get a 1/2 inch, a 1 inch, a 1.5, and a 2 inch. And you can put it on the scale under the document camera. I don't have them with me right now, unfortunately. And you can show that the mass goes up by cubes. 1, then 8 times as much, then 27 times as much, then 64 times as much, right? Okay. Why is the new area? Oh, that's a mistake. I need to fix this, okay? That's a mistake. It needs to be the new volume, so I need to fix that. Has this dependence on it? Hopefully that's fixed by the time you see this video. Why? Because all volume equations have a cubic dependence on length, right? Okay, so that's why that is. All right, so that was all about geometric scaling. That's a skill I would want to make sure students start off on if they haven't done it any earlier in the year. They're going to really need it here in fluids. Okay, density, it's, what can you say about it? I know how packed in matter is, right, okay. The density of an object depends on the substance the object is made of, right? And then if you want to have them write an equation here, then what you can say for an equation, you can say something on the order of, density is the ratio mass per volume. But I'm actually not ever going to write this. I'm going to rarely write it like this. I'm sorry, my handwriting is terrible. So this is not my favorite way to write the density equation. It's not wrong. It's just that you're going to see me more likely write mass equals density times volume. Why do I write it this way? The reason I write it this way is because you can screw students up on this. You can say that, try writing this on the board and then say this to your students. Say, okay, I'm going to fill up a cup of water halfway. Is the glass half empty or half full? You can have some little joke about that old saying, right? Well, what if I change the glass from being half full to being all full? Then I doubled the volume. What does that do to the density? And I bet you'll have students say, oh, yeah, that's half the density because you doubled the denominator. No, it's twice as much mass. The density didn't change because the substance is still the same. You can gyp students on this. You can make them say double volume is half density. No, what we're going to say is that if mass is density times volume, double volume is double mass. You see how it's a lot less difficult? It's a lot more difficult to get rooked on this one, right? That if you'd write it this way. And also, the way that students think when they see an equation, they automatically think this. They think that the quantity on the left is the dependent quantity, and these two things are independent. So if they saw this equation, they would think that the mass and the volume together choose the density. That's not how it actually is. The density is chosen by the substance, and the volume is chosen by how much you have of it. Those are two separately decided things. And the mass is determined by the density of the volume. That's why a lot of people write not F net equals MA, but they write it A equals F net over M, because this shows the correct cause and effect relationship. The acceleration is chosen by who is doing the forcing and who is being forced, okay? You can't push me hard enough to make me skinny. I'm a fat ass because I eat too many chocolate bars, okay? So I choose my mass. I don't care what other people say. Your weight problems are your fault, okay? I choose my mass, and whatever pushes on me chooses my force. So these two things together choose the acceleration. Here, your students think that the mass and the acceleration together choose the force. Do you see how that's not the correct cause and effect, right? That's not the correct cause and effect dependence. So I'm a big mass equals density times volume person. The symbol that we use to represent density is rho, the Greek letter rho. Row, row, row your boat. The Greek letter rho is the symbol that goes right like an R. The units for density for us are going to be kilograms per cubic meter. In chemistry, it's grams per milliliter or grams per cubic centimeter. So I want students to be aware that we're using different units. And because water is 1 gram per milliliter, or you could say 1 gram per cubic centimeter, I would tell your students that these two are the same thing. A milliliter is a cubic centimeter. Like, that may not be an AP physics thing that they have to worry about, but that's important things for them to know in life. In my opinion, it's 1,000 kilograms for every cubic meter. Okay, so they need to be able to know that. And I think the AP physics exam will just tell us that. I don't think the AP physics exam is ever going to mention specific gravity, but I want my students to hear about it for like 3 minutes, just so that they know that if they ever hear it in a future physics class, they'll know what it is. So specific gravity is, and I just call it SG, that's the ratio of the object's density to water's density. So if you measure your densities in grams per milliliter, grams per cubic centimeter, then the specific gravity is the same as the actual density of the object, right? So mercury is 13.6 grams per milliliter. Well, then its specific gravity is also 13.6. And notice that there's no units because it's a density divided by a density. But the density of mercury is 13,600. So 13,600 kilograms per cubic meter. 1,000. The specific mercury, so even it says here, like, if the specific gravity of mercury is 13.6, what's its density? Well, it would just be water's density times specific gravity, 13,600, right? Kilograms per cubic meter. Okay, the density of ice. Okay, so then if that's the density of ice, 917, and water is 1,000, 917 over 1,000 would be 0.9117, and notice that there's no units on specific gravity. Here, you would do the specific gravity, 13.6 equals the density of mercury, Hg, over 1,000, which is density of water, and you just cross multiply, okay? Now, how could we measure the density of an irregularly shaped object where the volume cannot be determined using a geometry formula, okay? Here's what you can do. What you can do, and there's a couple of ways you could explain this, but what you can do is you can have a tank of water, okay? And we're going to fill it up with water, okay? And we're going to mark on there with like a marker on the side where that water is, okay? So this is before. And then what we're going to do is we're going to immerse the object in the water if it sinks. It has to be able to sink. And then the water will now be at a higher mark than it was before. The water will be at a higher mark than it was before. Okay, if you know the area of the base, then you can find this volume is the same as this volume. So the volume that the water went up is the same as this volume. So you put the object on a scale to get its mass m, okay? Then you submerge in the water and see how high the water rises. We're going to call that delta H. So this right here is delta H. Okay, multiply delta H by the area A of the base to get volume V. Okay, V is, area times delta H. And then the density would just be the mass over the volume. Okay, which you would have the mass from right here and the volume from right here. Okay, now and then this is something students should already know, but just make sure they know if it's less dense than, if the object, let's say, if the object is less dense than the fluid, the object floats, right? And if the object is more dense than the fluid, the object sinks, okay? Like they should pretty much know that already. Okay, I'm hoping they would know that already. Okay, on the molecular level, why do denser fluids sink below less dense fluids? This is kind of difficult to understand, but the idea that the objects, molecules, and the fluids, molecules, both feel downward gravitational force. So the molecules of the object, the molecules of the fluid feel a downward gravitational force. Whichever is denser, the object or the fluid, right? The molecules feel more force and are the ones that go down. So if an object floats on water, it's because the water is being pulled down better than the object is. And so the water goes underneath the object, and that's why the object's on the top. But if the object is denser, then the object's molecules are being pulled harder than the water's molecules, and the water's on top because it's being pulled less by gravity, and the object's on the bottom, which is why it sinks. Like that's what I kind of want students to get across from that. Okay. Okay. If an object is made of pieces of different substances, such as a person made of flesh and bone, both of which have different densities, how can an average density? So I want students to know that every average in the universe is a total divided by a total. So in the case of their average grade, it's the total number of grade points they got over the total number of points they could have gotten, times 100%, of course, right? Well, with average density is the total mass of the entire object over the total volume of the entire object, right? Okay, so total mass over total. So muscle and bone sink, fat flows. Water is neutral because water has the same density as water, right? So when a human jumps into a lake, if they're very muscular or have very dense bones, this average density could be higher than that of water, and they might sink, right? But most students have enough fatty tissue. I'm not saying that they're fat, but they have enough fatty tissue that their total volume exceeds their total mass enough that the average density will be less than that of water. Sorry, I'm recording this after school and the lights are going off on me because they want to save energy, right? Okay. Why a boat can be made of steel, which is more dense than water, and yet the boat can float in water? Well, why that is because most of the boat's volume is empty air, which is far less dense than water, okay? So if you do average density, okay, what would you do? You'd have to do the total mass of the steel plus the total mass of the air, grand total, over the total volume, and that would be less than water's density, right? That would be less than water's density. But if you fill a steel boat with water, now it's not the mass of air, it's the mass of water. And so replacing, that should be a capital R, replacing air with water makes the average density more. And when the average density is greater than the density of water, then the object sinks. So I want students to be thinking in terms of average density. Okay, we're going to continue pressure next time, but first, the next video you'll see is me showing you some density-related activities.